Hello everyone, my name is Eleni and I will talk to you about our work with Clément Moulin-Frier on an evolutionary model of construction. If I ask you what is evolution, then probably I will hear the words natural selection, genes, inheritance, because indeed evolution is the process with which characteristics are inherited from parents to offspring through genes under pressure such as natural selection. And usually in both artificial and natural studies, we tend to reset the environment when we go from one generation to the next. And this choice is probably due to an assumption that has been crystallized in the modern evolutionary synthesis, which is not so modern because it happened around the middle of the 20th century, that agents modify their environment, but this process has a way smaller effect compared to natural selection, so we can safely ignore it. But since then, a lot of people have been questioning this assumption. And indeed, if we look at nature, then we will see that there are species that modify their environments to a large extent. And some species are particularly good at accumulating modifications with time and complexifying their environments, sometimes to such a large degree that they cannot deal with it. And so for the past decades, people have been working on the extended evolutionary synthesis, which, among other ideas in evolution, wants to introduce the concept of ecological inheritance into the evolutionary theory. And so that niche construction is seen as the reciprocal process to natural selection, and it is of equal importance. In both natural and artificial systems, we often see that environmental diversity plays a big part. For example, in the evolution of our own species, in the appearance of our own lineage of our species about 5 million years ago in East Africa, it is hypothesized that this happened during a period of very high climatic instability, which caused the fragmentation of the area into multiple niches that had different resource availabilities. And then in artificial studies, we have algorithms such as quality diversity, which explicitly design for a diversity of behaviors in a population. Or we have meta-reinforcement learning, where we train an agent on a diversity of environments in order to improve its ability to react to unseen situations. And in nature, organisms can respond to this kind of environmental diversity in different ways. They can specialize to a specific niche. They can become behaviorally plastic, which means that they can have mechanisms such as learning in order to adapt throughout their lifetime, or they can adapt at an evolutionary timescale through mutations. And in addition to becoming adaptable, they can also niche construct. And niche construction is an umbrella term that can include a variety of strategies. For example, maybe an organism is increasing the capacity of the environment in order to reduce competition for resources, for example, through agriculture. Or maybe it is performing negative niche construction, which is reducing the capacity of the environment in order to push out competitors, such as for example, pine trees, they spread the needles in order to increase the probability of fire. Or they may modify the environment to bring it closer to what they like, such as aquatic earthworms modifying the consistency of soil. And in this work, we wanted to have an evolutionary model where we can observe behaviors that look a bit like the ones we see in nature. And we wanted to keep it simple in terms of computational complexity, so it is not an embodied environment, it's an abstract one. But it is a complex model because it includes interactions between adaptability, environmental complexity, and niche construction. And there's been works that have studied like different parts of this picture, but in this work, we wanted to study all of it because we think that we can understand niche construction better in this way. So in the next slides, I will describe how we model the environment and the individuals and the agents, and then I will show some simulations. So in order to capture diverse environments, we design them having multiple niches that are arranged in a latitudinal model, where a niche is described basically by its location, its vertical location. And a niche is characterized by its environmental state, which has two components. It has the intrinsic part, which can be seen as the one that is not controllable by the agent. For example, resource availability due to climatic conditions. And this one is constant with evolutionary time, and it only depends on the location of the niche. And nearby niches that are next to each other, they only differ by a small constant amount. So there's some smoothness. And then we have the niche constructed part, which is the result of agents living in this niche and niche constructing, which we accumulate across generations, applying some constant discount factor. And in order to model adaptable agents, we use plasticity, where we adopt a tool from ecology called tolerance curves. This is a mathematical tool that is used to describe how the fitness of a genome changes as it is positioned like in different environmental conditions. So basically, a tolerance curve is a normal distribution that has a mu, and a mean, and a standard deviation. And the mean denotes the environmental conditions where the organism the agent has the highest fitness, which we call the preferred environmental state. And then the standard deviation describes how quickly the fitness drops as we move away from it, from the preferred state. So if you have a small sigma, then you're a specialist agent. If you have a large one, then you are a plastic. And in this case, imagine we have these two agents and they have the same preferred, they have the same mu, the same preferred state, and they are in the same location in the environment. And then if the environmental state in that location is identical to their preferred state, then the specialist is going to have much higher fitness than the plastic one, which captures the cost of plasticity. But if for some reason the environmental state changes a bit and becomes different from the preferred one, then the plastic will outcompete the specialist, which captures the benefit of plasticity. And we model evolvability is basically the mutation rate, and we jointly refer to evolvability and plasticity as adaptability. And then another parameter we studied in this model is the effect of the selection mechanism. We have two selection mechanisms. We have global selection, which is basically how we usually do survival of the fittest in artificial evolution, where the fitness of an individual, of an agent, is its average fitness across all niches. So we use we look at the genome of the individual, and using the tolerance curves, we can evaluate its fitness in every niche, and then we average over all niches, and we do this for all agents. And then we pick them for reproduction proportionally with a probability proportional to their fitness. And when we pick an agent for reproduction, we place it in one of the niches it can survive in randomly, and then its niche constructing genotype is expressed. It modifies the niche, and then it has two offspring. And then we do this until the capacity of the environment is filled. And then we want to contrast this with local selection. And in local selection, instead of your fitness is not your average fitness across all niches, but you reproduce independently in each niche. So we go sequentially through all the niches. We compute the fitness of all the agents in it. And then again, we reproduce them with a probability proportional to their fitness. And different niches, the capacity, different niches have different capacity. The capacity is proportional to the environmental state, and environmental states are higher in the north. So different capacities. And we see that in this case, an agent can reproduce more than one niches if it is plastic. So there is a benefit to plasticity. And this sort of local selection was inspired from algorithms such as quality diversity, where we have local competition. For the simulations, the way we do it is that we have some hypotheses that we want to study, and then we choose the parameters that we're going to study in each simulation, and we don't do an explicit analysis of all the parameters of the model. So one of the hypotheses we wanted to test is whether environmental diversity is necessary to study niche construction. And in this case, we compare a setting where we have one niche and a setting where we have 100. And we see that in the case where we have one with the blue, then the population goes extinct very early. So what happens is that they start niche constructing positively. This increases the variability in the environmental state. And so they respond by increasing their plasticity in order to adapt. But then at some point, the variation becomes so large that they cannot cope with it anymore, so they go extinct. Whereas in the case of 100 niches, although they have a similar levels of niche construction as average across agents, because they're dispersed in the environment, the absolute amount of environmental variability is smaller, so they can survive. Another hypothesis was whether niche construction can favor adaptability. So for this case, we compare between a population that has niche construction activated, the genome, which is the orange one, and one that where the genome is deactivated, the blue. And we do the study both for global selection and local selection. And we see that in both cases, adaptability increased, but in different ways. In the case of global selection, we got an increase in plasticity. And in the case of local selection, we got an increase in evolvability. And then this is for local selection, for global selection. Here, before, like the previous plots I showed were averages across trials. So in this one, we look at a specific trial because then we can get more intuition about what is happening in the population. And we have these heat maps where on the columns are generations. So we have like evolutionary time progressing. And the rows are the index of the niche. And the color of the heat map is the amount of total niche construction in this specific niche at this specific generation. So we can get an overview of how the population is niche constructing and how it is dispersed. And in this case, we see that we have some negative niche construction. At the beginning, it becomes being negative, and then this pushes the population to the south. And then we see this interesting oscillating pattern where the population is negatively niche constructing in this narrow stripe. Then at some point, this niche becomes uninhabitable because when you're negatively niche constructing, you're reducing the capacity. So they need to move out of it a bit, stay there for a bit, and then at some point, the niche becomes inhabitable again because there's the discounting factor of niche construction. And they continue doing this for some time until at some point they start niche constructing positively. And this creates a change in the environmental state that they cannot cope with because their plasticity and evolvability is very low. So they go extinct in this case. And this is the case of local selection, where we see that the heat map looks qualitatively different. Here, like everyone was like gathered in a narrow area of the world. And here we have them like being spread out. We have parts where there's like positive niche construction and negative niche construction, and there's variability with time. And the interesting thing in this case was that we measured the variance of niche construction within its niche at its time, and we saw that it is 2 orders of magnitude smaller than the one we had under global selection, which indicates that the agents that are inhabiting a narrow area of niches, they can coordinate their niche construction. And this helps diversify the environment further and explains why we also observe higher diversity in the population, higher genomic diversity in the population under local selection. So there's more simulations in the paper if you want to take a look. But to summarize, we observed a rich set of behaviors and dynamics in the population, and we saw that there is a complex interplay between environmental diversity, adaptability, and niche construction. So it is better to study them together. And one interesting thing is that environmental diversity was necessary, but then once it was there, then we saw that niche construction remained bounded, although we didn't add an explicit cost state. And in future work, we would like to move to more complex embodied environments where we have agents that are navigating grid world and they're collecting resources to see if our empirical conclusions they also apply in this case. And to do this, we have implemented this large-scale grid world where you can have thousands of agents moving around. And yeah, as a general closing note, we think we would like to encourage more studies of niche construction in AI and ALIFE, because one of the things we often say we want in AI is to have open-endedness. We want to have more complex environments, and then maybe niche construction is the way to do this. That's it. Thank you.